In this demonstration, you'll learn how to set up a steady-state thermal simulation to study the distribution of temperature in the model when a heat flux, convection, and radiation are applied. I'll start by selecting a simulation process template from the study panel on the left here. I'm going to select the thermal template. I'll leave the default physics type of thermal only and accept the default selection for the options list so that automatic contact detection is performed. In creating my simulation process, the first thing that I'm asked to do is select a geometry. I'll select the Design Modeler Geometry file for the curved 3-part pipe. AIM loads the geometry and sets up a simulation process, which will define everything I need to do for a steady-state thermal analysis. The geometry is now loaded. AIM has automatically created the physics solution process, which involves the geometry import, meshing, physics, and results. Here is a summary of all of the tasks along with their status. These tasks are also shown in the workflow window in a data flow diagram format. My physics task, the red exclamation mark here, is telling me that the physics task needs more information in order to complete the simulation. I'll click on it to go into the physics task. You'll see that a lot of defaults have already been set up for me. Material assignments, physics options, and solver settings. You can also see that the 2 connections were created for this case. Here, I need to add some boundary conditions. First, I'm going to add a heat flux to the face of this exposed cross-section. I'll use the face selection filter to select the face. Then I'll add the heat flux boundary condition from the context menu. I enter the magnitude of this boundary condition and press Enter. The boundary condition should now be up to date. Note that the heat flux value is also shown here in the heat flux panel. Next, I want to apply a convection boundary condition to the inner faces of the 3 cylinders. First, I'll need to hide the outer faces of these 3 cylinders. I'll then select the inner faces and right-click to add a convection boundary condition. I'll enter the values for the film coefficient property and the ambient temperature property and press Enter. The values are shown in the convection panel. I now want to add a radiation boundary condition to the outer faces of the 3 cylinders. First, I need to show all of the faces again. Then I select the outer faces. Then I right-click to add radiation. I'll enter values for the emissivity property and the ambient temperature property and press Enter. I am now finished with my boundary conditions. You can see I have defined 3 boundary conditions: heat flux, convection, and radiation. Now I'll update the physics solution task by right-clicking it in the workflow view and selecting Update. Because the meshing task was also ready, it will be automatically updated first. Once the meshing task is updated, AIM will move on and update the physics solution task. Everything's updated, so now I can go to my results. I'll first need to evaluate. Then I'll expand the results heading and click to view the results. The template has already inserted 1 contour result for temperature. This shows the distribution of the temperature throughout the model. This concludes this demonstration of an end-to-end basic steady-state thermal analysis in AIM.